So we've sort of taken a detour here and started talking about the Steenrod algebra. And again, I suspect that this is familiar to a lot of you, but remember that we're going to want to use the Steenrod algebra in our Serre spectral sequence computations. So it's worth sort of making sure that we're all on the same page and know how to play with these kinds of things. So I want to continue that detour a little bit and talk about some unstable modules over the Steenrod algebra. And to do that, or sort of to look at our first example, I'm going to define the total square. I'm not sure that this terminology is necessarily common, but let's call it that for now. So this is just going to be Squa. This is going to be a natural transformation from the cohomology of x in mod 2 coefficients, where x is some space, to the cohomology of x in mod 2 coefficients, and all this is supposed to do for me is collect up all of the squares. So this is defined by, if I want to evaluate it on some cohomology class, then I'm just going to take the sum over all I of square I of x. So normally when we look at cohomology, we really only consider homogeneous elements, right? This is a graded ring, but I only care about the homogeneous things because those are the things that have topological meaning to me. And this total square is, of course, not homogeneous. It's going to give me a bunch of classes in various degrees because the square i's raise the degrees by I. But then I can pick out the homogeneous pieces to learn something about the square i's. Also, remember that our cohomology of x is an unstable module over the Steenrod algebra in the sense that the higher squares vanish. So each sort of square I is, well, what should I say? X has some degree. It should be some homogeneous element in the cohomology of x. So it has some finite degree. And so all the square i's after that degree are just going to be 0. And so this infinite looking sum really terminates as soon as, after I get to the degree of x. Okay, and the Cartan formula, which told us how to compute the squares on a product, you can use that to show that this total square is a ring homomorphism. So that's really the reason that it's nice to collect all of these up together. We get this nice ring homomorphism from the total square, whereas our square i's, of course, are not. Okay, so an important exercise, maybe let me star it, you should definitely do this if you haven't done it before, is not to compute the cohomology of RP infinity. I was just about to say compute the cohomology of RP infinity in mod 2 coefficients, but of course we know that. So that's just z mod 2 adjoin x, where x is a class in degree 1. And what is the exercise? Actually, it's to use this total square to show that we know how to compute the square i's. We know how to compute square I on any class here. Well, remember, I only care about homogeneous classes in cohomology, so those all look like x to the k for some power k. And what does square I do on that? Well, it should take me to k choose I, x to the k plus I. Okay, of course, the x to the k plus I makes sense. The square I takes me up by degree I. And then this coefficient, of course, we should take mod 2. We're in mod 2 cohomology. So there you're going to want to use that Pascal's triangle mod 2 or whatever your favorite way to compute coefficients, these sorts of binomial coefficients. In any case, use the square, use that it's a ring homomorphism, and verify this. It's a very good exercise. So I want to investigate this a little bit more deeply because, I said I think the pictures are very helpful. And so let's draw a picture of what this looks like. I guess I'll start here. This is going to be 1. And then I'll have x and x squared and x cubed and x to the 4th and so on. And maybe let's stop there, but of course this will continue. So let me actually get the labels out of my way. So I'm just sort of drawing the cohomology. Make sure you can read that. I'm drawing the cohomology of RP infinity poorly. Okay, and of course this continues on forever. And I'm going to do the same thing that we did before. So a vertical line is going to mean square 1. I'll try to keep track of my colors, but at the very least a curved thing will be square 2. And then let's go ahead and work out what that looks like a little bit here. So if we believe this formula, then square 1 of x to the k is supposed to be k choose 1 mod 2 x to the k plus 1. Okay, and again, I find it very helpful to have my mod 2 Pascal's triangle here. So I'm going to draw that, at least a little bit of it. So here this is, whoops, whoa. Okay, I keep somehow hitting something strange. Sorry about that. So this is the line where I look at 3 choose I, right? So that's 3 choose 0 on the left, 3 choose 1, 3 choose 2, 3 choose 3. Okay, so I just like this because I can read it right off, but do it as you will. The moral of the story is that if I take k choose 1 mod 2 and I want to get something non-zero, then k had better be odd, right? And that's really just sort of this diagonal, oops, in my Pascal's triangle. So, okay, that tells me that, well, of course, square 1 of x is x squared. And I knew that anyway because the squares are an approximation to the cup square. And this is in the right degree. Okay, so I've got square 1 on x is x squared, but I also know that square 1 is 0. So, of course, square 1 on x squared was going to be 0. That makes sense because it's even. So I'm going to get this sort of alternating kind of thing. Okay, great. I think that was not so interesting yet. So let's look at square 2 on x to the k. Well, this formula is going to tell me that I should have k choose 2, x to the k plus 2. And of course I know that square 2 on x squared is supposed to be x to the 4th because it generalizes the square. And if I look at 4 choose 2, I guess that's the line right below here, 4 choose 2. Sorry, I should be looking at square 2 of x squared. So that's 2 choose 2, and 2 choose 2 is 1. Okay, anything choose itself is 1. Whew, thought it was all messed up there for a moment. Okay, so good news. Square 2 of x squared is indeed x to the 4th, and the formula agrees with that. But now if I look at square 2, say, of x cubed, I'm going to have 3 choose 2. So 3 choose 2 is right here. Okay, yes, indeed, I do have a connection there. So it must be that square 2 of x cubed is x to the 5th. So I gave myself a little bit of space there. Now again, this is all pending that you've done this exercise and proved this formula, which you can find in Mosher and Tangore if you get stuck. But okay, so I do have that connection. I look at square 2 of x to the 4th. Now that's 4 choose 2. Oops. Now that's 4 choose 2, and 4 choose 2 is indeed 0. Okay, so I shouldn't have a square 2 connection coming out of here. There's nothing there. What about square 2 of x to the 5th? Well, I just follow that down. Okay, that's 0, but I can see the next one is going to be a 1. So there is a square 2 connection. I just lost track of it. I think that we were up to x to the 6th. we'll have a square 2 to x to the 8th, and so on. Okay, and you'll see this kind of repeating pattern, so it's sort of nice to draw this out for a little ways. I see this sort of square 1, square 2, square 1, square 2, and so on. Okay, great. So this, of course, continues, but then we'll be off the page, so let's just stop there. Another thing we could do is square 4. Remember that we don't need to draw square 3 because square 3 is just square 1, square 2, not particularly interesting and already in the picture. But square 4, well, square 4 should square x to the 4th, right? That's its job. And I guess, let me write. You can, of course, substitute 4 into this formula, but that'll be k choose 4, x to the k plus 4. Okay, great. So I do know for sort of multiple reasons, because 4 choose 4 is 1, and because square 4 is supposed to be the thing that squares the class in degree 4, that indeed we have a square 4 connection. Let me draw it off to the side this way. Okay, and so on. So this is an unstable module over this Steenrod algebra in the sense that I know that square 4 on anything in lower degrees should have been 0. I guess I didn't even say that as I was drawing this picture, but of course square 4 on x is 0, and I end up taking 1 choose 4. Okay, that must be 0. But that's just for degree reasons, right? Because we have this square I is 0 once your degree is too high. Okay, and so I can start to draw these pictures of modules over, unstable modules over the Steenrod algebra. And a stable module would just mean that I don't necessarily have that kind of restriction. But the cohomology of any space is going to look like a module, an unstable module over the Steenrod algebra. And we can learn a lot from these kinds of things. So let me maybe move on from this picture and try to actually learn something from this. Well, one thing you can easily prove. One thing you can easily prove using unstable modules over the Steenrod algebra is that you can look at the suspension of CP squared, and at first glance, it might look like it's S3 wedge S5. It seems possible, but in fact, it cannot be. So let's see why that is. Well, when we look at the cohomology of CP squared to begin with, that's just z adjoin x. I could work in mod 2 coefficients, but I can also work in integral coefficients. So that's z adjoin x mod x cubed. And now that x is in degree 2. Okay, so when I look at the cohomology of the suspension, well, I'm just going to have my z in degree 0. It's connected. I've got a z in degree 3 and a z in degree 5, and that's it. And notice that the cut products here have to be trivial. Of course, if I took something in degree 3 and took its cut product with itself, I'm going to land in degree 6, which is 0 anyway, but also we know this is trivial because it's the suspension of something, and cut products are always trivial on the suspension. Okay, so this is the same ring as the cohomology of the wedge. Oops. So I'm just going to have a z in degree 3, a z in degree 5, and that's, of course, I have a wedge, so there are no interesting cut products. That's all I get. Okay, so you might think, well, these could be homotopy equivalent spaces, at least. But we can use the Steenrod algebra to rule that out. We know that the Steenrod algebra acts on the cohomology of CP squared not in integral coefficients, but in mod 2 coefficients. So we've got our Steenrod algebra acting there. And what does it do? Well, we know square 2 of x had better be x squared, because that's in the right degree. Okay, and we could start to think about what the other squares do. When I look at the cohomology of the suspension, well, again, the Steenrod algebra acts there. It's just the cohomology of space in mod 2 coefficients. But the fact that the squares commute with suspension, I'm going to abuse notation a little bit here and act like I can suspend x. I just mean sort of chase that through the suspension isomorphism. So if I look at square 2 of that suspension, then that's going to be the suspension, again, chase it through, of square 2 of x, and that's the suspension of x squared. So here, this is my sigma x, as I'm calling it, that generates degree 3, and this is my sigma x squared that generates degree 5. So what I have there is a square 2 connection, right? So if I wanted to draw the cohomology of the suspension of Cp squared, I'd have, something in degree 0, and then I'd have a square 2 connection from degree 3 to degree 5. But if I draw the wedge, well, I have the same classes, but no Steenrod algebra connections. This is just a wedge. So Steenrod algebra acts completely trivially. Okay, so this proves already that the suspension of Cp squared cannot be the wedge of these spheres, even though as rings their cohomology looks the same. Now, in fact, we can take that argument further. So what if we take the kth suspension of Cp squared? Well, we're always going to have this Steenrod algebra action, right? This thing is nice and stable. So this is actually never a wedge of spheres. I don't have to think about what degrees my spheres live in, but there's the obvious ones that are possible, and it better not be by the same argument. I keep suspending, and I'm still going to get that square 2 connection. And I'll never have that square 2 connection in a wedge of spheres. Okay, so another way to interpret this is that we're saying the attaching map eta from S3, that's the boundary of our 4 cell, to S2 when we build Cp squared, this never becomes null. Now I'm calling this eta because this is our Hopf map, typically called eta. I guess eta doesn't stand for Hopf other than in homotopy theory. But okay, so after suspending, this thing can't die. I'm saying square 2 detects eta in a way. Okay, and so pi n plus 1 of Sn isn't 0 for n greater than or equal to 2, and that's how we learn that pi 1 stable had better not be 0. Now, I think I told you that it's actually a copy of Z mod 2, and this Hopf map in pi 3 of S2 generates a copy of Z, so we'll see that it's going to surject onto the Z mod 2, and we'll learn that through our Serre spectral sequence computation. But for now, certainly we learned that there is something in pi 1 stable, okay? And I think this is kind of a neat way to do that using the Steenrod algebra. Okay, let me sort of give a little bit more terminology at this moment so that I can kind of wrap this story up in a nice way. So we'll say that square n is decomposable if it decomposes. So what I mean is we get a sum of compositions of smaller squares. Remember, the degree still needs to be n, so I'm going to write this in this way. So I have some square k, where k is less than n, so something of smaller degree. And then the square I of k, this could just be some sequence of squares. So maybe just to have an example, you play around with the Adem relations. and you see, oh, 2 is less than 2 times 4. Okay, so I can do an Adem relation, and I calculate my binomial coefficients, and I'll get square 6 plus square 5 square 1. So that was really a square 6 square 0, right? And so this tells me, by solving for square 6, that square 6 is decomposable. It's really just the sum of square 2 square 4 and square 5 square 1. Since I'm working mod 2, I don't have to worry about minus signs, which is nice. Okay, so another good exercise, again, if you haven't thought about this before, or if it's been a while, is that square n is indecomposable if and only if n is a power of 2. So remember we said that our squares 2 to the I or 2 to the k gave us a set of generators for this D-Nord algebra. And so now I'm really saying they're indecomposable generators, and that's really why. So to do this exercise, you should use the cohomology of RP infinity as a module over this D-Nord algebra that we just looked at, and also the Adem relations. Okay, and then the nice sort of corollary to round this out is that if you look at the cohomology of some space in mod 2 coefficients, and you see that it's just polynomial on one generator, then now of course RP infinity is an example here, but what we can learn is that the degree of this generator had better be 2 to the k for some k. Okay, so how is this a corollary? How does the D-Nord algebra help us with this? Well, the proof is quite short. I always leave the longer ones as exercises for you. Not that this previous one was particularly long or hard, but this one's a one-liner, so I'll prove it. Square n of x had better be x squared if x is in degree n. Right? That's one of our properties of the squares. But if n is decomposable, then I should split it up into a bunch of compositions of smaller squares, right? And all the lower squares are 0. Why is that? Well, they should factor through 0 because I know the cohomology is just polynomial on x. So there's nothing between x and x squared, right? And so if I had something like, I don't know, I knew that square 3, I was looking at square 3, then it would factor square 1, square 2, and that square 1 would already, well, I guess square 2 first would hit 0. So the point is this factors if n is decomposable. So it must be that our square n is indecomposable and it's a power of 2. In fact, you can limit this a little bit further, but that uses some other techniques and will take us sort of afield here. So let me just stop there. But I will say, you know, these are kind of some nice facts just to really get us used to this D-Nord algebra and how we can play with it and what it can tell us. But again, we're working towards, let's use this D-Nord algebra to look at this air spectral sequence and what it can tell us there.